with all facilities in that. We have a dinner in there during the star party, and they have ablution blocks, showers, toilets. There's one field that would be, that's probably 3 acres, and there's trees on 4 sides of it. It's cleared, and that's the telescope field for the duration, and people camp in the trees around the periphery of that. And many years ago, we always have a professional come in and give a speech at our dinner, and we had Ed Stone, then director of JPL.
Right. That was a long time ago.
A long time ago. And I'll never forget, I was, this is really basic imaging. I'd ordered a an infrared surveillance camera from Oatley Electronics in Sydney, a software company. And I had a VHS output, 20 frames a second. And I had an old VHS video recorder down my observatory. And I was just messing around with it, looking at the moon. Well, not looking at the moon, looking at a crater on the moon at 20 frames a second. And something went straight through the center of the field of view. If you blinked, you missed it. It was less than half a second. And I processed it and printed out the individual frames, the 5 frames of the 20 that showed the object. And the first frame, if you've seen Independence Day, of course so. So the shadow of the alien spacecraft crossing the crater on the moon, that's what it looks like. You see that over, going into this crater. And then the second frame, it's that, so it's got bigger. I'll never show anyone the third frame, because the third frame, like a passenger jet, straight through the center of the field of view, so highly magnified that when the wings come off the fuselage, you only see to the very edge of each engine pod, and then the last frame is up close and personal of the aviation light under the tail. Anyway, I'm showing this Ed Stone, the first 2 printed frames, and he looked at me and said, young fella. Well, I was young then. That's a very long time ago. He was sure that I doctored them. He's sure they couldn't possibly be real. But the best part was when you looked at the video, so the jet whistles straight through the dead center of the field of view, straight across this crater. But when it's gone, like the jet wash from the engines appears to go out and ripple the surface.
Very cool. Very cool.
Super cool, super cool. I contacted Air Services Australia in Melbourne. Like it came from the south heading north over Broken Hill, where we were out in the outback. So I know it's probably directly above Australia. You go up there, Osaka, maybe Japan. It could have been going there. And I wanted to ID the aircraft. I had the precise time, obviously, and I thought, well, I'll print a sequence of these images and I'll label them. Well, they hung up on me. I got the impression that they thought I was a terrorist wanting information on
flight
paths of domestic aircraft. But the old Ed Stone, young fella, doctored it.
Hey, Clyde, are you...
Trevor,
are you the guy who was sending Saturn reports in all the time, and I think NASA or JPL brought you to California?
Yeah, NASA gave me security clearance to go to JPL.
Right.
I supported the Cassini mission for the last 10 years of his life.
Yeah.
That photograph of you is from JPL.
Yeah. When I found my first electrical storm, I'd graduated 2 years earlier at Swinburne Uni. Yeah. And I knew Professor Fred Watson and Dr. David Malin from the Anglo-Australian Observatory. And I contacted them about storm that I'd imaged. And they pointed me to the Cassini Laboratory for Operations, Central Laboratory for Operations, Cyclops, Carolyn. Yeah. Well, from that, Georg Fischer contacted me, and he worked on the Cassini radio and plasma wave science team, then out of the University of Iowa. And this was the 23rd of February of 2011. And he told me that he knew there was a storm there, that it started late in November the previous year. But to that point, Cassini had only imaged it once, and he was totally dependent on ground-based amateur data to track the storm. He had Marc Delcras in France, Ralph Vanderberg in the Netherlands, Crisco in the Philippines, and would I like to be part of that group?
Oh my.
So from that point on, I was a part of the team, and every time he detected, he called them SEDS, SEDS, Saturn electrostatic discharge. When he detected, the radio data from the electrostatic discharge from the lightning down deep within the atmosphere, he contacted our group, with the challenge being to hunt down the optical counterpart of his radio source. Well, it was coming from like 300 clicks down within the atmosphere, traveling about 100 meters a second, bursts through the top cloud layer, different stuff from deep within the atmosphere. I would image a white spot, accurately measure the latitude and L3, and only then could he do his analysis on the propagation of the radio waves through the atmosphere, and continue to do that for the entire life of the Cassini mission.
I think you were spotlighted on 60 Minutes Australia.
Yeah.
And also, when you were up here, did you get a chance to do any nighttime observing?
That was Hawaii. That's another story. No, well, I was only over in the States for 3 days, would you believe? 3 days. But I got to meet Carolyn, and our journalist interviewed Carolyn and Trev from Broken Hill on the floor of Mission Control spaceflight operations at JPL. Big thrill. But I got heaps of publicity when I found that first storm internationally and here in Australia. Actually, NASA TV did a piece on it, and the major metropolitan papers here also did stories, sent journalists out. We're a long way. We're over 1,000 kilometres west of Sydney. We're in the bush. Anyway, right. The journalists from The Age, the Melbourne metropolitan paper, before it was published, was a full page, and she rang me, and she had some questions for a little CV, top right-hand corner, one of which did it have any unfulfilled ambitions. I said, Struth, I'd love to observe with the Kex, some of the greatest optical telescopes on planet Earth. Well, that was 2 years after I graduated, and my final unit instructor was Professor Duncan Forbes with astrophysics and supercomputing at Swinburne. Well, wow. Caltech run the Kex, Swinburne have a supercomputer. So Swinburne is the only Australian university with a time allocation on the Kex, 20 nights a year. Caltech get to crunch data on Swinburne's supercomputer. Well, Duncan rang me, said, Trev, I'm taking 2 PhD candidates to Hawaii. We've got 2 nights on Keck 2. Would you like to come? So I came my way, but I got to go to Hawaii with a professional research team, drive through the cumulus cloud layer in a diesel 4-wheel drive, to the summit. Yeah. I'll never forget it. I think I'm soft. I got out the vehicle, standing in front of Keck 1 and Keck 2. One of the units that I did at uni was the history of astronomy. I'm thinking of the Herschels and Kepler and, everybody that put the steps in motion to where I was standing, right in front of the pointy end of optical astronomy on planet Earth. I had tears running down my face. I'll never forget it. Never, ever forget it. It was just an amazing, amazing experience. Yeah.
Fantastic.
What kind of work did you do when you were, before you retired?
I started in 1969, an apprenticeship in fitting and machining with Conzinc Rio Tinto on a zinc mine, big zinc mine in Broken Hill, and I spent 34 years working on the mine. I got into astronomy very, very late in life, and when I finished work on the mine, my gorgeous and adorable wife, she said, well, you got to do something, you'll go mad. And I was into astronomy, but I had no clue as to why the stuff I looked at through my telescope looked the way it did. You know, like what's actually happening? Why does the Great Orion Nebula, what's happening there? Anyway, I applied for a postgraduate degree with Swinburne University in Melbourne. Like, it was an online degree. Postgraduate, I left school after only fourth year high school to work in the mines, so I wasn't sure they'd even accept me. So I ran it past Professor Fred Watson and David Mail, and they'd been to my observatory. They came out and visited me. They knew how enthusiastic I was and what I'd built. And they were very supportive of me having a crack at it. Well, it took me 2 years, but I graduated with straight high distinctions. My lowest unit mark was 91. Graduated in March of 2025, and in September we got a letter, not an email, but a snail mail letter from my faculty inviting me to Melbourne, where the head of school presented me with an award for excellence for being the top graduating student in my degree program, which was very humbling, you know, like
Congratulations.
a long way from working in the mines. And
Yeah.
you know, my work is published in peer-reviewed journals around the world, you know, and it keeps my brain active. I love it.
Congratulations. Congratulations.
We'll keep it active. Yeah, definitely when that paper gets released, let me know and we'll.
Yeah, I will. You'll love it.
I bet I will. Let's
It's
chat
very
about
Great
it.
story. Trevor, where are you? Are you in Australia?
I am, think 1,200 kilometres west of Sydney.
So that puts you near Darwin or Perth?
No, out
They're
out
further
the
away,
outback.
aren't they?
Oh, that's even further. That'd be more northwest. Well, I'm just
How far from Adelaide?
out in the middle.
Okay.
It's very
you by-
flat. It's really good for astronomy. Like, we have because it's flat and desolate.
Mhm.
So the weather systems traverse our continent west to east, and the high pressure systems often track inland. And when a high pressure system comes over my town, Broken Hill, it pushes the
Okay.
jet north and south and gives me really stable air over the top. So generally we have very low relative humidity. There is no light pollution. I've had professionals come out here to visit, and they always remark on how blue the sky is. You know,
Okay.
much bluer, a deeper blue than near the coast. You know, no pollution. I've had heaps of TV crews come out here, and the cameramen always comment also on the clarity of the sky out here. It's just good for what I do.
Oh, yeah.
How far are you from
I'm up
Ayers Rock?
to 9,700 data sets now. I've got uploaded to Augustine's P-Vol database. Mostly, well, probably about 75% Saturn, 25% Jupiter.
All right. I used to travel to Sydney and Melbourne back in the late 70s, working with a guy by the name of Ben Douglas. If you know BJD Electronics, they were a hi-fi retailer.
Yeah.
All
Yeah,
right.
no, but
Anyway, it's a beautiful country.
yeah, we enjoy it out here.
I'm only laughing because you're safe from all the craziness of Americans right now.
Oh, mate. Yeah.
We don't have time for that. Quick. Oh, thank
No, we
God,
don't.
it's 4 o'clock. Tim, don't let me
Yeah.
say
I'm
anymore.
going to wait a few more minutes. I'm waiting for a couple people to get
All
in.
right.
Need to see their names. Yeah, Trevor, next year you got to do a paper for the conference.
Because?
You
Oh, for
present a paper next year.
This year.
Next year's conference.
No,
20
it's 2026 conference.
I mean, this
The
conference, so
2026 European Planetary Science Congress.
I know, but you should present at this conference
here.
next year.
Oh,
Oh,
I would hate to let you down, Tim.
yeah, I don't think that's possible.
Oh, I tell you what,
We have Ken Pachedley, so you can't let me down.
Well, we have. I don't know whether you've heard of him, John Sarkisian. He's with the CSIRO in Australia, and he's the chief science officer at the Parkes Radio Telescope.
Oh my!
And he runs the Central West Astronomical Society. And he invited me to go and speak at a convention over there. I'm big on PowerPoint presentations, and the highlight of my PowerPoint presentations is a rock and roll animation of the greatest electrical storm mankind has seen in our solar system, obviously on Saturn, like in January of 2011. And behind that slide, as the slide is playing, it looks like a great comet in the atmosphere. It totally encircles the planet. It's stunning. And behind that, Georg Fischer sent me a 32-second byte of the radio data recorded by his instrument on the Cassini spacecraft of the electrostatic discharge happening within that storm that you're looking at.
Wow.
I get excited about things like that.
I can't tell.
Oh, I'm sorry.
What time is it for you? What time is it for you?
So it's 8:30 in the morning. It's 8:30 Sunday morning.
Okay, so you're in the future. How's it looking?
Oh, well, the future, mate. We've had so much cloud. Although this morning we've got blue sky.
Yeah, but I mean generally.
With the
See, we're-
I've only had, I think 2 days in May for imaging Saturn because of the amount of cloud we've had. It's so unseasonal, but anyway.
Anyway,
Trevor, are you on the west side or the east side of Australia?
Central.
I'm a bit east of the centre.
Oh, okay. You're more
Like
inland.
1,200 kilometres west of Sydney.
Oh, okay. Okay. So you're like between halfway, between the coast of the Sydney and central Australia. You're like halfway.
Yeah. Oh, well, a bit less than halfway.
Okay.
Trevor, how have the fires been out there?
We don't have fires out where we are, mate. This is desert.
So they don't affect you, what's going on in Sydney and Melbourne?
No,
Okay.
no. Although
It's a big continent, I know.
it's very big. Yeah.
All right.
So yeah, that's right.
Dude, I went
We've
to
had a-
Woomera for the
We had
eclipse
a
back
rain
in about
of recent
2002.
times, and the desert's blooming, and the desert doesn't look like desert currently. It's actually, quite green, which is very unusual.
Wow.
Ho ho. Okay, Tim, take it away.
Yeah, I win for one more person.
Oh, okay.
Just give,
Yeah, the reason I asked about the time is that it's just after 7 p.m. Saturday evening here in the East Coast, eastern part of the United States. That's why I was kidding around with you about you're in the future for us. And we're in the past for you.
Yeah, well, I've got the AGM at our bowling club in about an hour's time.
Wow. There's 11 hours ahead of us on the east coast of the United States. 11 hours.
And now you're in the middle of winter.
The middle of winter. Well, so I've got a sleeping bag. This is an alpine jacket. I put a balaclava on, beanie over the top of that, woolen gloves, and I climb into a sleeping bag that I zip right up to my throat. I have my hands out to operate my computers, a double-decker computer hutch a laptop in the top with software that runs. I pulled a 10 by 50 finder scope to pieces and machined an adapter. I'm a very well equipped machine shop, have my own lathe, Anyway, so I machined an adapter to take a CCD camera. It gives me a low power wide field view, and then below that I have my fastest computer, which Anthony Wesley tells me is steam driven. All my gear's old, and yeah, he does. He says, "That's steam driven, Trev." That drives my fastest computer that runs the software for my main imaging camera, which is on 2,000 power. I image at 2,000 power. Yeah, very narrow field of view. So not degrees of arc, not minutes of arc, but seconds of arc field of view, like about 3 times the diameter of Saturn outside ring to outside of the rings. That's the field of view. So,
hey Tim, let me interject here. Tim, I got the pop-up again. I'm just going to have to let it sit. It says update begins in 13, 12 seconds, whatever.
Okay, whatever.
I'll let it go. It'll not quite finish whatever the update is, and then it goes away, but it happens spontaneously, and it's a real pain.
Okay.
And it warns me not to interact with my browser. Navigating away may interrupt the update and cause data loss. I mean, and there's the progress bar, okay? And it never gets completely to the end.
I don't know what to tell you, Ken.
I always blame Bill Gates.
What's that?
I always blame Bill Gates.
All right. I think I'm not going to wait anymore. Let's get started. I want to thank everybody for the last 2 days of the conference. It was a lot of fun. Some excellent presentations, most of them. I know all of them. They're all very good. We recently had 2 members receive kind of cool honors. Jim Tomney received a minor planet designation. Congratulations, Jim.
Oh,
It's very cool. That's what it says. Thank you to
thank you guys very much.
Thank you to Rick.
That was a
Thank you
big
to Rick
honor.
Hill. Thank you
That's
to,
Teske. You got the Teske one up.
no, I don't.
Yes, you do.
Now you have to go out and look for it.
No, it's right. I'm looking at. Oh,
Yeah.
okay. Well,
Oh,
that
it's
was-
about 23 magnitude or something like that.
Jim, you have to change your last name.
Here's a Teske.
Teske.
The Teske.
That's Teske. That's me.
45638 Teske.
Well, that one's David's.
Right?
Nope.
Alan's Teske. Yay.
David
Yeah.
Teske is an American amateur astronomer, etc.
Thank you, Ken.
All
All right. So you guys didn't see. Let me see. Hang on. Let me look here. I'm new here.
You don't have to worry about it. I'm sure they believe you.
Hang on. Let me.
Yeah, but he wants to show it.
Yep. Shoot. Why isn't that showing? Huh.
There's David Teske.
Yeah. Don't do this to me.
Oh, that's
Why is it showing Teske? All right. Never mind. Screw it. All right.
that's terrible.
I know.
And this is
Sorry.
better than the International Star Registry, I understand.
Yeah,
Yes,
this
yes.
means a little bit more. All right.
Thank you very much.
Yeah. Well, congratulations, guys. All right.
Congratulations.
We have a special recognition we'd like to start off with. Board Member Emeritus recognition to Julius Benton. It's my honor to recognize a gentleman whose name has been deeply woven within the history, leadership, and scientific legacy of the ALPO. For years, Julius Benton has served the organization with extraordinary dedication, professionalism, devotion, and his contributions as board member, section leader, observer, author, mentor, and friend helped shape the ALPO to the organization we know today. Julius has long represented the very best in what the ALPO stands for: careful observation, scientific discipline, historical continuity, service to others. His work with the planetary sections, his leadership, and his steady guidance have benefited generations of observers. He not only contributed observations and reports, but helped preserve the standards and traditions of the ALPO. Organizations like ours are built by people who give their time, knowledge, and heart over many years, and Julius has done exactly that. His service has been marked by wisdom, humility, and a deep commitment to the mission of the ALPO. Today, we recognize Julius, what he has done, and also what he means to the organization. In appreciation for many years of distinguished service and dedication, it's my privilege to present Julius L. Benton with the honorary title of Board Member Emeritus.
And here is the plaque, and I'll read the text. In grateful recognition of his many years of distinguished service, leadership, and dedication to the Association of Lunar and Planetary Observers, and for his lasting contribution to its scientific mission and legacy, Board Member Emeritus. And I will get this out to him. I'll be getting it out on Monday.
Okay. All right. Next up. The Mike Reynolds Astronomy Outreach Award. This award is presented to an individual for their significant contribution to popularizing astronomy, recognizing their outstanding contributions to public understanding and appreciation of astronomy. Past recipients include David Levy, Praveer Hysini, and Scott Roberts. This year's recipient is a respected astronomy writer, educator, lifelong advocate for observational astronomy, based in Duluth, Minnesota. He spent much of his career working as a freelance science writer and planetarium educator, helping thousands of people develop a deeper appreciation for the night sky. For many years, he worked as the educator at the Marshall W. Allworth Planetarium at the University of Duluth, Minnesota, where he taught astronomy to students, to public lectures, and observing sessions. He's widely known to the amateur astronomy community for his writing. He's a longtime contributor to the Sky and Telescope magazine, where his articles have guided readers through observing comets, meteors, planetary events, and other celestial phenomenon visible to most amateur astronomers. He's also been a guest on the Observer's Notebook podcast. He's highly regarded as Astro Bob in his astronomy blog, and he regularly publishes articles explaining current astronomical events and how observers can see them for themselves. His writing style and practical observing encourages readers to step outside, explore with binoculars and telescopes, and through his articles, lectures, outreach work, he's inspired countless of people to develop an interest in astronomy and to participate actively in observing the night sky. His work exemplifies the spirit of public astronomy outreach, helping bridge the gap between professional discoveries and enthusiasm for amateur observers. His dedication to sharing the beauty and excitement of the night sky has made him one of the most trusted and beloved voices in amateur astronomy today.
Here you go. I'll read that for you as well. The Association of Lunar Planetary Observers, the Michael D. Reynolds Astronomy Award for 2026, Bob King, in recognition of your decades of inspiring the public to explore the night sky through your writing, lectures, and dedication to observational astronomy. The Association of Lunar and Planetary Observers proudly presents this award for astronomy outreach. Through your work with Sky and Telescope magazine and the Astro Bob blog, you have helped countless observers discover the joy of looking up and understanding the universe above them. There you go.
Thank you. And Bob, he's been at all the talks the last 2 days, and I was waiting for him to show up, and I haven't seen him show up yet. So I texted him like an hour ago and haven't heard back. So congratulations, Bob. Okay. Next up, the Peggy Haas Service Award. The Peggy Haas Service Award was established in 1997 to recognize members of the ALPO for outstanding service to our organization. The current ALPO director solely selects the recipient for this award, who can recognize any ALPO officer, board member, volunteer staff member, or non-staff member who has contributed to outstanding service to the organization. The awardee receives a lifetime membership to the ALPO. Each year, the Association of Lunar Planetary presents the Peggy Haas Service Award to recognize an individual whose dedication, volunteer spirit, sustained contributions have strengthened our organization and community it serves. Peggy Haas embodied the very best of the ALPO: quiet dedication, generosity over time, and committing to help the organization and its members thrive. The award honors those who follow the same tradition and service. Our recipient this year is someone who exemplifies those qualities. For many years, he's been a steady, dependable presence within the ALPO. Through his observations, support of observing programs, and willingness to contribute whenever help is needed, he has demonstrated the kind of commitment that keeps volunteer organizations like us alive. Those who know him understand his contributions have not always been the most visible, but they've been deeply meaningful to the ALPO community. His enthusiasm for observing and his willingness to share knowledge, support fellow observers, and made him a valuable member of the organization. Tonight, we recognize that dedication.
And here's Mr. Venable's plaque, which reads, for those who can't see the screen, the Association of Lunar and Planetary Observers, the Peggy Haas Service Award for 2026, Roger Venable, in recognition of your dedicated service, commitment to observational astronomy, attention to detail, and your many other lasting contributions to the Association of Lunar and Planetary Observers and its community of observers, especially to the Mars section. We proudly present this award. Your volunteer spirit and support of the ALPO mission exemplify the tradition of service honored by this award. Congratulations.
Hey, Roger.
Thank you so much. I want to say that I'm flabbergasted. I certainly didn't expect this. And it is a great delight to me to be recognized in this way. Thank you so much.
Well deserved.
Great, Roger. Congratulations.
All right. And the final award for the evening, the Walter H. Haas Observers Award. The Walter H. Haas Observers Award is bestowed annually to the amateur astronomer for excellence in observational solar system astronomy. This award is named for our founder, the original executive director, and was established in 1985. The selection of this award is conducted by a committee convened by the chairman. The composition of the committee changes from year to year so that the responsibility of the selection is shared by a wider group of members in the ALPO that are all well qualified, while allowing others to vote one year or another and to be considered for the award in another year when not serving on the committee. I'd like to thank the 2026 members of the Walter Haas Award Committee, myself, Wayne Bailey, Clyde Foster, Bob Lunsford, Frank Malello, Greg Shanos, and Roger Venable. This award is given for the excellence in solar system amateur astronomy. The award itself consists of an engraved plaque. The awardee also receives 2-year complimentary membership. It's a great honor to present the 2026 Walter Haas Award because it recognizes an observer whose work reflects the highest traditions of the ALPO: careful observation, persistent scientific value, and the willingness to contribute to those observations. This year's recipient exemplifies all those qualities. Gary Walker has distinguished himself as an outstanding planetary and imager. His work represents the kind of careful, consistent, high-quality observing that's long been the heart of the ALPO. His planetary images, his contributions to the ALPO observing programs, and his willingness to share his knowledge with others, Gary has made a lasting contribution to our organization and the study of the planets. Gary's work reminds us that amateur astronomers continue to play an important role in planetary astronomy. With dedication, skill, and persistence, observers like Gary document the changing faces of the planets, provide valuable records that can be studied, compared, and appreciated for years to come. The spirit of Walter Haas lives through observers who not only look up, but record, analyze, and contribute, and teach. Gary Walker has done all that. On behalf of the Association of Lunar and Planetary Observers, it's my privilege to present the 2026 Walter H. Haas Observer Award to Gary Walker for recognition of his outstanding achievement in planetary observing, imaging, and his dedicated contributions to the ALPO.
Thank you very much. I'm flabbergasted. Can you hear me?
Yeah.
Yes, sir.
Okay. This is unbelievable. I appreciate this so much and totally out of the blue. So thank you very much. I very much appreciate that and hope to continue to contribute in the future.
Get this up here.
Congratulations to all of you.
Just keep sending me your Mars images.
Will do.
Yeah, here we go. All right. Congratulations to all, and thank you for those that sat on the committee and worked with me on it. All right. This brings us to our keynote speaker. It's my pleasure to introduce our keynote speaker for the 2026 ALPO conference, David Kring. Dr. Kring is a principal scientist of the Lunar and Planetary Institute and leading authority on impact cratering, geological evolution of the moon, and other planetary bodies. His work has helped shape our understanding of how impacts have influenced the history of our solar system. He's perhaps best known for his groundbreaking research on the Chabot crater, which provided key evidence linking that impact event to the extinction of our dinosaurs 66 million years ago. Dr. Kring has also played an important role in shaping scientific goals for future lunar exploration. His work has contributed to planning for missions associated with NASA's Artemis mission, helping scientists identify the most scientifically valuable regions of the moon to explore, as well as prepare for humans to return to the lunar surface. Throughout his career, Dr. Kring has also been a strong advocate of scientific value of the moon as a record of early solar system and gateway to future exploration. Today, he'll share his insights into lunar science, exploration of how the moon continues to reveal the history of our solar system. Please help welcome me, Dr. Kring, as our keynote speaker.
Good evening. Thank you, Tim, very much. I'm going to begin to share my screen and then pull up my slides. So just stand by.
Okay.
Okay. Have the slides come up on your end, Tim?
Yes, I have.
Okay. Very good. Well, it's certainly a pleasure to speak with this group about one of my favorite topics, and that is the Artemis exploration program. And I'm going to try to narrow the focus a little bit on the region that we'll be exploring initially, and then try to give you a ground level view, which may be a new way of looking at the moon, and hopefully a way of looking at the moon that will become familiar to all of us. But it's a way of looking at the moon that's been foreign to us for about 50 years. So hopefully it will prove insightful. I have left plenty of time at the end to answer your questions, and you should feel free to answer questions about what I am speaking about or other lunar exploration issues that maybe I don't address. Okay, so since you're a group of observers, I wanted to start with this picture produced by an observer. Tom Glenn produced this wonderful image of the lunar South Pole. And you can see Shackleton Crater, which is at the South Pole there at the top of the image. A couple of other features that will be important this evening will be Malapert Mountain. And you'll see in some of the additional charts references to Amundsen and Faustini and some of the other structures in this wonderful photograph. It also illustrates three attributes of this region that are going to be very important to the Artemis exploration program. One is, as you can see, it is an impact crater terrain. There's just no getting around it. And so impact cratering processes have shaped this portion of the moon and will govern what astronauts are able or allowed to do. Because it's impact crater, it's topographically complex. And I'll speak a little bit more about the dimensions, both horizontally and vertically associated with that topography, but it is going to also constrain and affect what it is astronauts are able to do. And then for those of you who are sharp-eyed, you see the shadows, of course, cast across the lunar surface. This being a polar region, some of those shadows can be quite long, and that is going to be another attribute of this particular part of the moon that astronauts are going to have to wrestle with. Okay, so let's move on to this next slide, which hammers at this issue of topography. So on the left side, I have drawn a topographic profile across Malapert Massif and an adjacent crater called Hallworth. This is using laser altimeter data from the Lunar Reconnaissance Orbiter spacecraft, which is still in orbit around the moon today. And then for comparison, on the right side, I have a similar topographic profile across Mount Everest. And so the takeaway is the topography at the lunar South Pole kind of dwarfs what we consider to be rather dramatic and challenging topography here on the Earth. It's also an ancient terrain, and in fact, far more ancient than any of the Apollo landing sites. And so here you see a diagram that along the horizontal axis plots time from about 4.56 billion years ago, the beginning of our solar system, to more recently, about 3 billion years ago. And it's divided up into the epochs that we use to separate the stratigraphy on the moon. And as you probably already know, that stratigraphy is defined by some of the largest impact basins on the moon. They redistributed debris across the lunar surface, basically resurfacing the moon. And so it produced characteristic stratigraphic horizons. Things that it buried are older, things that it didn't bury are younger. And this is a stratigraphic scheme that was developed by Don Wilhelms and others at the USGS Astrogeology branch here in Flagstaff, which is where I'm speaking from this evening. On that timeline, I have indicated the representative ages of some of the Apollo landing sites. So you can see Apollo 11, where we started, actually has a couple of different ages in the vicinity of that landing site. Apollo 12 landed on a much younger terrain. Apollo 14, an older terrain. 15, again, a younger terrain. And then with 16 and 17, we returned to the older terrains. Now, I want to make the point, for those of you who are familiar with the Apollo landing sites, that the Apollo 16 landing site is our best proxy for what it is we're going to see in the Artemis exploration zone. And in fact, I think I may have spoke too quickly with that first graphic. The Artemis exploration zone is in the vicinity, at least the initial one, is in the vicinity of the lunar South Pole, and specifically within 6 degrees latitude of the South Pole. So it's an impact crater terrain, as I've mentioned before, and an impact cratered highland terrain, which is why Apollo 16 is our best proxy for that. Even though, as you'll see in this chart, it's a little bit younger than the terrain that's to be explored initially with Artemis. And that's blocked out in that gold region. And it's going to cover a range of ages, all of which at this point in time are estimated until we actually collect samples from the surface in the Artemis exploration zone and return those samples to Earth where they can be analyzed in our laboratories. We won't have precise ages for any of those terrains that I'll be speaking about this evening. Okay, and just for reference, most of the rocks that we'll be collecting in the Artemis exploration zone are older than anything that we can collect here on the Earth. And that's very important if you actually want to understand what the Earth, how the Earth was affected or how it evolved in the first 500 or 600 million years of its history. You really do have to go to the moon to tease out that record. Okay. Now, here's an attribute that I've mentioned before, and I think it will be familiar to you since you're a group of observers. The poles are kind of a special region on any planet that's in the ecliptic. The sun is not rising to the east, passing overhead and setting in the west, and on the moon, producing a 14 Earth day long day and then 14 days of night. Rather, the sun is migrating circumferentially very close to the horizon. It's just circular. I'm stumbling over the words. Drawing a circle around the pole. And because this is a crater terrain, that is going to produce shadows in the craters, and some of those shadows are going to be permanent. And so one of the famous attributes of this region are permanently shadowed regions, which is one of the features that is driving NASA and other nations' space agency to target this portion of the lunar surface. Here is a movie that was generated by the Goddard Space Flight Center several years ago, and it illustrates what the sun's passage around the pole does to the shadows. So there are long shadows, there are deep shadows, that is, these permanently shadowed regions. And in stark contrast, it's hard to pick them out in this video, but there are a few points that are nearly always illuminated. And that NASA has focused on as important because it may be a near continuous source of solar power. And in fact, that's driving NASA's exploration effort right now, is the accessibility of resources. And there's two prominent ones. The first one is access to solar power, which you can see illustrated here. Another one has to do with the availability or accessibility, or I should say the potential accessibility of volatiles. And so I get to that issue with this slide. Those permanently shadowed regions, because they do not see the sun, are very cold, and they remain very cold unless they see any bouncing solar sunlight from the walls of the adjacent craters. And so this is a little cartoon that illustrates that. On the left side, you see the freezing point of water, the average surface temperature of Pluto, and then the coldest annual average temperature on the moon, which is about 38 Kelvin. And on the right side, you see some very important temperatures, sublimation points of water, ammonia, carbon dioxide. And from this graph, you can see that in those PSRs, those permanently shadowed regions, water and ammonia and carbon dioxide might actually persist as ice. And if that is available, that would be another important resource. And why? And I'll just illustrate that with water. If there is water, it's an important crew consumable for both drinking water and oxygen. Water is also a very effective radiation shield. On the moon, you're sitting there naked, exposed to cosmic and solar radiation, and so you're constantly worried about the hazards of radiation. And so you're trying to find different mechanisms to shield yourself from that radiation. I won't have an opportunity to speak about it, but we, about 15 years ago, built a prototype rover for the astronauts. This was a pressurized rover, and the roof of that rover would hold 6 inches of water to shield the astronauts inside the vehicle. Water can also be a very important rocket propellant, separating the oxygen from the hydrogen to do so. Okay, so this is another look at that Artemis exploration zone. That's the region within that white circular line. And within that region, you'll see that there are several boxes. Those are candidate landing regions that NASA has identified as their primary targets, potential targets. Now, you can see that these regions are fairly large. They're at least 15 by 15 kilometers. And within any region, there may be multiple landing sites. But these are regions that, for both resource-driven issues and communication issues and landing availability or accessibility issues, have risen to the top of NASA's interest. Okay, so at the center of that circle, we again have the Shackleton crater, and you'll see there in the crosshairs that is right on the rim of Shackleton crater. That's the South Pole. And very near the South Pole is one of these candidate landing regions called Connecting Ridge. And to illustrate, or to introduce, if you will, the lunar surface, I'm going to focus for a moment on that region, Connecting Ridge. This is an oblique view of Connecting Ridge that we produced several years ago. So you can see Shackleton crater there in the distance. SP is the South Pole, which is right on the rim of that crater. There are also 2 sites identified in this image. One is Site 001, which is right on the ridge, and then Site 004, which is on the rim of Shackleton crater. Those 2 sites were identified quite early. I want to say in about 2010, in the midst of the Constellation program, as being 2 sites with tremendous amounts of illumination. So in those 2 sites, you have access to solar power about 86% of the time, which is very good, which means that you don't have to have a tremendous amount of battery capacity to survive the short periods of time when you do not have access to solar energy. Now, one of the things I want you to draw your eye on is not only that is Shackleton crater an impact crater, but you can see the ridge itself is just speckled with impact craters. And impact craters are both challenges and sites of opportunity. They're natural drills into the lunar surface, and they bring material up from depth up to the surface where an astronaut can collect it, as well as harboring some of these permanently shadowed regions. So I have a little movie here. I think I have enough bandwidth for this. For those of you who are unfamiliar with impact cratering processes, we did a computer simulation of the Shackleton crater impact event. And on I have to say, we did a large number of these simulations to try to determine what the best impactor diameter was and what the best impact velocity was. And you'll see there in the caption beneath the movie that, and I'll play the movie 1 or 2 more times, that our best fit to the topography of Shackleton crater is that it was produced by a stony asteroid about 1.5 kilometers in diameter, hitting the lunar surface at 15 kilometers per second. Now, the other thing I want to point out, and I'm going to show this just one more time, the crater, of course, is a crater because material is excavated, and you can see it rising in this curtain off to the sides, and it lands on the surrounding terrain. And so this is very important. There's about 150 meters of ejecta sitting on connecting ridge. And of course, that was self-evident to all of us geologists who study impact cratering processes. But it was astounding, at least to me, that it was not self-evident to others who were involved in mission planning. But as this movie illustrates, that clearly that connecting ridge is covered by impact ejecta from Shackleton. Okay. So this is a cross-section, a geologic cross-section of Shackleton crater. And you can see there in purple along the surface of connecting ridge, that's the ejecta that you just saw generated when the impact occurred. There's also a dashed line from one rim of the crater to almost the other rim, a little bit below it. And that line illustrates the point below which Shackleton crater is permanently shadowed. And so the floor of Shackleton crater is going to be very, very cold. And the floor of the crater is going to be composed of a breccia. That is a type of rock that is produced by the fragmentation of older rocks and then rejumbling those fragments and redepositing them. And so there's going to be a very thick lens of brecciated rock in the floor of the crater and little pods of impact melt scattered throughout it. Okay. So Shackleton crater, let me just point this out. Again, it's a simple bowl-shaped crater, right? I mean, it looks like a cereal bowl. And so we call these simple craters. And meteor crater on Earth is our best analog for a simple crater. This is a wonderful view of simple crater, of meteor crater, excuse me, which is in northern Arizona. For those of you who are familiar with Lowell Observatory, this is just 45 minutes away. It's about 1.2 kilometers across and about 180 meters deep. Because it is the world's best preserved impact crater, it was an important training site for Apollo astronauts. And here you see there on the left, Gene Shoemaker training the Apollo astronauts at the crater. And for the same reasons, it's still a location where we train astronauts. And so there on the right-hand side is me with several astronauts in the 2009 class on the floor of the crater. And so basically every class from 2009 up to the present is now going to meteor crater. In the midst of the shuttle program, they didn't do that, but I was asked to help revise the astronaut training program in the midst of Constellation. So we put meteor crater back into that training curriculum. Okay. That said, even though it is a wonderful analog for craters like Shackleton on the Moon, it's a tiny, tiny, tiny crater. So here's a close-up view of Shackleton crater, and there is a little black dot showing the size of meteor crater. As I said, meteor crater is about 1.2 kilometers across, whereas Shackleton crater is about 21 kilometers across. 21 kilometers right at the upper limit of the transition between simple craters and complex craters on the Moon. Craters that are much larger than Shackleton will begin to have central peaks, and even larger basins will then have a peak ring. Okay, so the scale of the features at the lunar South Pole are can be different. That is not to say there aren't meteor crater sized craters in the Artemis exploration zone. In fact, you can count them. There is approximately 3,200 craters the size of meteor crater in the Artemis exploration zone, and about 5,200 and I believe 41 craters in total within the Artemis exploration zone. Again, it is an impact crater terrain. Okay, so here's another way of looking at the scale of Shackleton crater. So here's again that cross section. It's a roughly 21 kilometers across, and it's 4.1 to 4.2 kilometers deep. And I was trying to find a way of explaining this to engineers who are involved in developing mission architectures, because it is, if you're not a geologist, if you're not a person who is constantly walking in and out of up and down mountains and in and out of canyons, it can bedevil you. And so here I illustrated that it's about 3.5 times deeper than the Grand Canyon, which is a feature that many engineers and other scientists who may not be field geologists can better grasp. So again, the topography is going to be challenging and is very dramatic. I point out in many of my public lectures that this topography, if it had occurred on Earth, would be a national or international park. Okay, so that's an introduction to the terrain that the Artemis astronauts are going to be exploring. And so you might be asking yourselves, what might be involved once they are on the surface? And so let's actually then spend the rest of our time taking a look at what they may or may not be able to do. Okay, and so here's that diagram I showed you a moment ago, and on it I've put a little gold box. I'm going to focus your attention on that gold box, which is in the middle of that connecting ridge candidate landing region. Okay, so this is that box, and for those of you who read topographic lines, you can see that there are little white lines, squiggly lines across that, illustrating the topography. And there is a ridge, a topographic high ridge, and that's going from lower left to upper right. And on that ridge are a series of white outlines, little areas outlined in white. And those are areas on that ridge that meet the requirements, the landing requirements for NASA's human landing system. The first human landing system is to be provided by SpaceX. The second human landing system is to be provided by Blue Origins, but both of them have to meet the same requirements. And those requirements have everything to do with slope and the size of the region with that slope, which needs to be ideally less than 8 degrees. So you can't land anywhere on that ridge. You can only land within those areas outlined in with white lines. Okay, so and there are some permanently shadowed regions within that area, and you can see one of them is circled there in blue. And so I'm going to take you, if you will, from landing site 6 to that PSR and try to address what's involved in that type of thing. So that PSR is about 60 meters in diameter. It's much smaller than Meteor Crater in size, but it is within 650 meters of location 6, and that's reachable by an astronaut. The walking EVA limit for an astronaut is right now set at 2 kilometers. So they can reach 650 meters without breaking the flight rules. And importantly, it is on a relatively shallow slope. There is a slope limit. Astronauts are not allowed to go, or for that matter, our vehicles are not allowed to go on slopes greater than 20 degrees. And if an astronaut is walking, we would very much like that to be between 0 and 5 degrees. And in that particular walk over to that PSR, there is only a 20-meter section that goes as high as 16 degrees. So it's well within the 20-degree limit, and the segment where the slope is very steep is very small. Okay, so we've developed these computational tools that determine the best path from the landing site to targets of interest or regions of interest like that PSR. And the goal of this computational tool is to minimize the metabolic workload on the astronaut. We do not want the astronaut to get too fatigued. And really importantly, we don't want their interior body temperature, their core body temperature, to get too hot, because that would create a medical emergency. So on the left is the idealized route for that astronaut or pair of astronauts in plan view. And then on the right is a route shown in an oblique view. Now, this program actually provides the flight director and others in the flight control room with a lot of other information that's very important, which I just illustrate here with a few diagrams. And in fact, the computer throws this up on the screen automatically, and so it's there for everybody to observe and track as the astronauts are going across the surface. But it provides their elevation, it provides their slope, it provides the temperature at the surface, it provides the illumination that's available along the route, and it keeps track of time, which is very important because, of course, the astronaut is in a spacesuit with a limited amount of consumables. Okay, so in this particular case, I'm illustrating an astronaut's route to one of these permanently shadowed regions. And ideally, if you're asking an astronaut to go somewhere, you want to evaluate the risks, the hazards. And so we developed a new image processing tool that allows us to see in these permanently shadowed regions. You may have read that you cannot see into these permanently shadowed regions, and that is sometimes true in the largest ones. But we developed an imaging technique using lunar reconnaissance orbiter camera images where we're very efficiently counting basically every photon that's coming out and being captured in the images. And so there on the right, you can see that we can actually see craters and boulders within that permanently shadowed region. So if we were to ask an astronaut to go into that permanently shadowed region, we know exactly what we're asking them to get into. And so here on the left is that same image, and then on the right is a little map showing where the craters and the rocks are, and where there's a little more light and a little less light, well, no light inside that permanently shadowed region. And so this is another tool that we've developed in preparation of this first landing. Okay, for time, I'm going to go past this slide because it basically repeats something I've already said. Okay, this is that diagram that I showed you before, and now I want to take you up to Malapert Massif, and we're going to dive into what an astronaut might do in a little more detail. And for those of you who are older enough to remember watching the Apollo astronauts on the lunar surface, this is going to draw you into some of the methods and activities that you witnessed them pursuing or doing in the late 1960s and earliest 1970s. Okay, so let's zoom into Malapert Massif, which you can see is, again, one of the high summits in the lunar South Polar region. And this is a cross section across it. If you focus first on the lower right, there is a similar diagram of the massif, and you'll see there's a white line across the massif, and then the diagram across the top is a topographic profile that follows that white line, and you can see it runs from the intercrater plains there on the left and ends in Haworth crater there on the right. And this, by the way, is to scale. There is no vertical exaggeration in this particular cross section. And NASA asked us to evaluate potential astronaut traverses on the summit of Malapert Massif, which is indicated by the star in that diagram on the lower right, and to actually design 3 notional traverses for astronauts, explore what the scientific opportunities were, and how they could best or most efficiently and most productively be explored while maintaining the health and safety of the astronauts. Okay, so the setup here is they've landed there on that star, and they're going to have a series of 3 EVAs, and I only am going to have time to illustrate one of those EVAs. Now, prior to the mission, we process every bit of orbital data that we have. This is a diagram that illustrates some of the things that we can produce when we process that data. There in the upper left is a blended hillshade with 2-meter resolution, spatial resolution. Then you'll see the topography illustrated there in the top center. You'll see slope there on the upper right. You see a map of boulders in the lower left. You see a radar image in the bottom center. And where you see the orange colors, that's roughness. That is a separate measure of where there might be boulders and so on and so forth. And then there is a formal terrain readiness there in the lower left, lower right, excuse me. And then here's some other diagrams that we produce pre-mission. An important one, by the way, is in the upper left. The blue region is the areas where the astronauts maintain visibility with the lander, which can be very important in orienting yourself on the lunar surface. The top center shows the areas where the astronauts and the lander have maintained visibility to Earth. So you have direct to Earth communication if you stay in that yellow terrain. And there's a few other maps that we generate in this pre-mission study. One of the features that I want to point out there in all of these is there is a crater there in the upper right of each of these panels. That was simply identified as an unnamed crater C when we began this study. Over the course of the study, we submitted a recommendation that this crater be called LAMU, and the International Astronomical Union approved that name, and so that crater now has the name LAMU. Okay. As before, we use our advanced imaging technique. So the floor of LAMU actually is a permanently shadowed region. And so we use that fancy image processing tool, and we can see that there are a few smaller craters on the floor of LAMU crater and lots of boulders. And so you can see with this technique, we're actually able to see boulders as small as 3 and 5 meters in size, which would be fascinating to study. Okay. We also did a model of temperatures on the lunar surface. And I'm just checking my time here, so excuse me. So so we did a model of temperatures, and all of these regions in blue on the same map are areas where water ice is theoretically stable. It doesn't mean water ice is there, but it's where it is theoretically stable. And so these are areas that NASA also has asked us to investigate. And so we did that in the course of the study and pointed out where the astronauts would have to walk if they wanted to probe those. Okay, so this is a 6-hour EVA. And so what that means is the astronauts get out and get into their spacesuits, leave the lander, and then they're on the surface working in their spacesuits for 6 hours. And in the left is the diagram that illustrates the traverse. There is a landing site area. They're kind of in the lower left. A lot of lines are radiating from it. And we're going to follow the path that goes to and returns from crater C or LAMU. As I said before, I only have the time to illustrate one of these EVAs, and this is the longest of the EVAs, and so it's the most interesting. I can use it to point out the most activities. Okay, now, before moving on to the next slide, I want to point out that on this traverse, there are a lot of green triangles. Those are boulders. Those boulders in this particular scene were excavated and tossed out of LAMU crater when LAMU crater was produced. And so these are very interesting, very valuable scientific targets. And so for sure, astronauts are going to be collecting samples from those particular boulders. And so, in fact, they actually drive the science for this particular EVA. Okay, so you might be asking, what are the astronauts going to be using for tools? And they're going to be using basically the same toolkit the Apollo astronauts had. It was a very robust toolkit. So they'll have hammers, they'll have scoops, they'll have tongs, a variety of tools that can pick up rocks, hammer or chip off rock samples off boulders, and collect soil samples for return to Earth. I should say that mass is always a very critical element. So these have to fit within the payload capacity for landing. But as you might imagine, all of these tools are going to be left on the lunar surface so that we can bring rock samples and soil samples back to Earth. Okay, now I want to address a point that seems to vex people and gets overly exaggerated. I showed you earlier in this presentation that diagram that NASA produced that shows shadows, circulating around the pole, and it kind of looks, depending on your point of view, it looks awesome or scary. So people will point out that this is a terrible environment to work in because those shadows are constantly shifting. You hear that, and it frankly drives me up a wall when I hear that, because in fact, I have quoted here one of these people who have spoken and said the lighting environment will change drastically within the course of one mission and even over sometimes the course of a spacewalk. Nonsense. Okay, so here I illustrate this with two pictures taken over the duration of an astronaut EVA. And as you can see from the picture, the shadow from this particular boulder hardly moves. And the way to think about it is the shadows on the moon in the polar region are swinging 28 times slower than they do on Earth. I'm a field geologist. When I go out in the field, at the beginning of the day, the shadows are, throwing east to west. At the end of the day, they're 180 degrees opposite, going west to east. It doesn't bother me. On the moon, in the South Polar region, the shadow is going to move, a fraction of a degree over the course of an EVA. And so it is really not going to be a problem. Okay, so let's now start this EVA, and the astronauts get out of their vehicle and they go to Station 1. Station 1 is a small crater. They're going to be able, it's a small young crater with fresh ejecta. And so they're going to be able to collect a nice sample there and some rocky nuggets from the soil and photographically document it just like they did in Apollo. And they can do all of that in about 27 minutes. Time is really important, as I said, because they are going to be consumable limited. Okay, then there's the traverse from Station 1 to Station 2. And here is an important point. There is science to be done on these traverses. And this is something that we're beginning to train the astronauts to do during the Constellation program. In that program, the astronauts we get in the rover I spoke about earlier, and they would simply drive in a straight line from Station 1 to Station 2, and they would be completely mum because in their mind, all of the activity was at the stations, at Station 1 or Station 2. But in fact, there is tremendous science to be observed and described en route. And in fact, you can probably enhance the scientific return of a mission by an order of magnitude if you pay attention and describe what you see between stations in general. And so we've asked the astronauts in this particular setup to actually take time to describe the terrain as they're going. That is particularly important on the second leg of this traverse when they are going through the boulder field near the rim of Lamu. We want them to describe those boulders because on the return, they're going to sample some of those boulders. And there's not enough time for them to sample all of them. And so based on their survey description to Station 2, while they're at Station 2, we will make decisions in Houston as to which boulders they will sample on the return. And so this is a way of enhancing the productivity of the mission. Okay, so then they get to Station 2, and they can't go in to this crater. Lamu is a very big crater. It's meteor crater in size, so there's no way that they can actually walk into it. It's also a permanently shadowed region, and it's basically at their EVA walking distance limit. And so all we can ask them to do for Lamu is actually to photo document the interior of that crater, which will provide us imaging at a higher resolution than we had from orbit and give us a really good view of what a modest sized PSR actually looks like. And of course, while they're on the rim, we'll ask them to collect rock and rake samples and to collect a scoop of the soil. And they can do all of that in 33 minutes. Okay. Now they're returning back to the lander and they're going to pass through this boulder field. And so stations 3, 4, and 5 are the same. They're going to photo document at each station. They're going to collect rocks from the boulders and collect them and return them to Earth. Now, you're thinking that's a lot of rock, and it is a lot of rock. Unfortunately, there's 16G here, so the rock isn't quite as onerous to carry on the way up to the lander. But I do want to point out that they did go downslope to this crater, and they are having to move upslope to return to the lander. We're very aware of that. I mentioned earlier that we are very aware of minimizing the metabolic load on the astronauts, and we were very aware that we want to make sure that their core body temperatures does not rise too high. And that's why we have most of the stations on the uphill segment. We've done tests with astronauts in Houston, which demonstrates that the hardest thing for astronaut to do is to climb a slope. Their core body temperatures actually has an opportunity to recover at a geologic station, even though they're doing geologic activity. And so that's why most of these geologic station activities are on the uphill portion of this slope. Okay, and so then they go to 6. This is important because it's farther away from the crater, and that means it's going to be a boulder excavated from a shallower depth. The boulders nearest the rim of Lamu crater will have come from the deepest part of the craters. And as you go uphill and greater distances from the crater, you're going to be sampling shallower and shallower portions of the crater. And then we get up to station, we do more of the same. And each of these, as you can see, is about a half-hour station. Now, we've asked them to collect a lot of rocks, and you're sitting there thinking, more gray rocks. Why do the geologists want more gray rocks? And so I want to speak to that issue for a moment, because it's not evident to everybody why these rocks are so important and why it is people like me think they're so beautiful. Okay, well, people like me actually get to look at these. We get to tear them apart, if you will, get to peer inside the rocks. And what you recognize and what you see when you begin doing that is you realize that these are not just gray rocks, they're actually quite beautiful rocks. And I'd like to illustrate that with some samples. So here's a wonderful sample from Apollo 12. This is what, when we tear into the rock and we make a thin section of it, this is 30 microns thick, and we plop it down on a petrographic microscope. This is what it looks like. You can see all of the individual mineral crystals within the rock. All of the most of the pinks and the yellows and the blues and the greens are olivine. There's a few pyroxene crystals in there, and then the large white and gray minerals are largely plagioclase crystals. But it's a wonderful view of what is a classic sample of basalt. All right, here's another example. This is another basalt. This is an olivine rich basalt. This is a high titanium rich ilmenite-bearing basalt from the Apollo 17 mission. Gene Cernan and Jack Schmidt collected this sample. And again, it's just absolutely like stained glass. And then here's a final one that I wanted to show you. This is another Apollo 17 sample. This is collected at Station 6. This is an impact melt breccia. This is the type of sample that we will probably see a lot of in the Artemis exploration zone. And again, to a geologist, we can use the colors and the shapes and the textures of these rocks to determine the minerals, the chemistry, the cooling rate of these rocks. And then we can go in and isotopically determine the age of the rocks and so on and so forth. So these are the rocks that actually tell us wonderful, wonderful stories. And so I want to point out some of those stories. Right here is some of the big ideas that emerged from the Apollo program, and they all come from analyses of the Apollo geologic samples. So I'm sure most of you have heard about the giant impact model for or hypothesis for the origin of the Earth-Moon system. The lunar magma ocean hypothesis. This is the idea that the moon was once surrounded by an ocean of magma. There's the lunar impact cataclysm hypothesis, which suggested that the moon and by proxy, the entire inner solar system was severely bombarded in the first 100 million years of solar system history. There's the impact origin of life hypothesis, which suggests that bombardment has everything to do with the early evolution of life and potentially the origin and early evolution of life. There's a more recent idea that's emerged, and that's the lunar magmatic hypothesis, epoch hypothesis. That's the idea that the South Pole Aitken Basin impact event, which produced a 2,500 kilometer, 13-kilometer deep basin on the lunar far side, actually generated a pulse of magmatic activity on the near side, and in fact produced the rocks that the Apollo astronauts collected. And then we've been getting better at analyzing the amount of oxygen and hydrogen and water in lunar samples, and therefore we're being able to better understand the origin of water both on the moon and on Earth. And that then gets us to this notion that has captured NASA's attention that this water, in fact, might be an important resource, one of two important resources in the lunar South Polar region. Okay, so I'm closing in on the end, but before leaving, I want to point out that there are a few architectural and operational deficits that still need to be addressed. We still need to improve surface and Earth-to-Moon communication. We still need to improve rather the amount of mass that we can return to Earth. We don't yet have mobility in the program that'll occur after missions with walking EVAs. We have a science back room rather than an integrated science and flight operations room. And that, I think, is going to affect productivity and location. What do I mean by that? Well, we did a 6-year study of the landing sites across the lunar surface and asking where on the lunar surface could you do the most science? And the answer was the Schrodinger impact basin, which is just outside the Artemis exploration zone. We are going to the South Pole not to maximize science productivity, but because of the potential of those resources, solar power and volatiles. That's something that you want to keep in mind. Okay, if you do want to know more about this information, my group alone has published over 24 peer-reviewed papers on this Artemis exploration zone, and they are available. The bibliographic details are available at the Center for Lunar Science and Exploration website. Also, if you want to learn more about training for these types of operations, there's 3 go-to places. One is my guidebook to the geology of Meteor Crater, also called Barringer Meteorite Crater. I've used this to train several classes of astronauts, and I've published this online. And so you can freely download this from the Lunar and Planetary Institute website. There's also a document that we were asked to prepare for NASA Administrator Bridenstine, Training for Lunar Surface Operations. That is also available for free download from the LPI website. And then I produced a monster volume, 578 pages long, I think, on astronaut training for operations and impact crater terrains. And that, again, is freely available for download from the LPI landing site. Okay, Tim, with that, I want to thank you and your audience, and I would be delighted to take questions. And again, you don't have to limit your questions to the material that I presented this evening. If you have questions about other aspects of lunar exploration, please feel free to voice them. If I can answer them, I will try to do so.
It was very good. Yeah, I want to mention that when the astronauts were orbiting the moon and we could hear them describing what they were seeing, it reminded me back to like Apollo 15, when Dave Scott was talking about that they were actually educated at that point. Early on, they weren't. And you mentioned Gene Schumacher. Yeah, he had a big impact with training the astronauts to learn to see. And then, of course, Harrison Schmitt, the geologist, went up at the end. So,
Yes. Yeah. All absolutely all true. Could not have said it better.
Is basalt on the moon different from the basalt on the Earth?
Yes and no. So how do you
Okay.
like that for an answer?
No, I can understand that.
Yeah. So a basalt by definition is an igneous rock dominated by pyroxene and plagioclase. And so to first order, okay, so you have a piece of basalt with San Carlos mantle nodules
Yes,
inside.
basalt with olivine.
Yeah. What
Nice
mantle
color.
nodules? That comes from San Carlos, Arizona.
No, I don't remember where it came from. I ordered it, from a rock and mineral store.
I'm almost positive that came from San Carlos, Arizona.
Okay.
So
okay.
yeah.
But it's
So
beautiful.
yeah. So basalt. So basalt is one of the most common lithologies on the rocky planets. So it's present on Venus. It's present on Earth. It's present on Mars. It's present on some of the minor planets. Vesta, for example, being a wonderful example. But it's different in detail.
Yeah.
So, for example, Gene Cernan and Harrison Schmitt collected those samples of high titanium basalt at the Apollo 17 landing site, and it has tremendous amounts of ilmenite on it in it. And ilmenite is a potential resource if we were to if we wanted to mine it. The titanium itself can be extracted, and the Marshall Space Flight Center engineers 15, 20 years ago printed spacecraft parts with titanium. It was a very early demonstration of tool making. And so that's the type of thing that they're doing on the space station as well. And it's certainly going to be a process or an activity that is deployed to the lunar surface. Also, you can chemically process ilmenite to release water. It is one of the mechanisms for making water on the lunar surface. The problem is basalt only covers 17% of the lunar surface.
Okay.
And none of those lava flows are in the South Polar region.
Okay.
So we're not going to be doing volcanism until we leave the initial Artemis exploration region. Now, at several times in the development of both Constellation and Artemis, the engineers have said, we can simplify our spacecraft designs if we know we're only going to the poles. And at that point, I have to jump up and down and say no. We really want to maintain global access. And so that adds flexibility to the spacecraft components, which adds some upfront engineering cost, but I think over the exploration period is going to dramatically reduce costs and enhance our ability to explore and make use of the moon.
Okay, thank you.
So let me follow on since I don't see another question popping up. The contrast to basalt on the moon is anorthosite. This is a plagioclase-dominated rock, right? It's the highlands. The basalt is the dark surfaces that you see when you look up the moon, and the highlands are dominated by anorthosite, largely composed of the mineral plagioclase. And there's going to be a tremendous amount of anorthosite in the South Polar region. In fact, we have using orbiting spacecraft data identified several large blocks of anorthosite right around the South Pole, both in the walls of Shackleton Crater and in the ejecta, the debris thrown out from Shackleton Crater.
What word are you saying? A northosite?
Anorthosite.
Could you spell that, please?
Yes. Anorthosite.
Okay.
Anorthosite.
Yeah.
Yeah. And for the Canadian, I don't know if we have Canadians, but Labradorite is a variety of anorthosite. It's a plagioclase rich, not technically pure anorthosite, but closely related to it. Anorthosite on the Earth tends to be very old rocks.
Okay.
And so they tend to be in the billion-year-old rocks. They tend to be, yeah, I'll just leave it at that. I don't want to get too deep into the complexities of their formation, but yeah, they tend to be very old rocks. And on the moon, they are the oldest. So, we have, 4.51 billion-year-old anorthosite in the Apollo collection. So they're going to be very old, very ancient. As I tried to allude to before, Artemis is going to be a more ancient terrain than the Apollo site. That doesn't mean we won't find rocks that are younger than we found at Apollo, because some of those craters are going to be young, but on average, Artemis exploration zone is very old.
Okay, I thank you very much for your talk. I enjoyed that. Are you talking about Artemis 4 or beyond or what?
So I was speaking about the first lunar surface missions, and I was very careful not to assign an Artemis number to it because the architecture has changed. I mean, if you had heard me speak, for example, at Lowell Observatory 2 years ago, I spoke very definitively about Artemis 3 being the first lunar surface mission. But at the moment, the first lunar surface missions are going to be Artemis 4. But that may change again. And so I was simply speaking about the first couple of lunar surface missions that are largely walking EVAs. Eventually, we will get mobility, we'll get rovers on the surface, and then the nature of the efforts will look more like Apollo's 15, 16, and 17. But today or this evening, depending on where you are in the world, I was limiting my description to the walking EVAs, which will occupy us for the next several years.
Okay, thank you.
And there's nothing like hematite or goethite, right? On the moon?
There's one geologist in Hawaii who thinks they've identified a little bit of hematite, but just a little bit, and it needs to be confirmed. So I see there's a hand up. So David Teske, I think it is.
Hey, thank you. Very interesting talk. I've always wondered with Artemis, you're going to land at the South Pole, and it clearly is a very rugged terrain. Wouldn't it be wiser to land in an Apollo area on a flat mare on the near side to test out equipment first?
Well, okay, so yeah, and yeah, I can't speak for NASA. So they're the ones that are making these decisions, and so I mean, certainly I work with NASA. My research is for NASA, but I try to be very careful not to pretend I'm speaking for NASA. And so they're making decisions. They were the ones that selected all of those candidate landing regions. Now, I know some of the people involved in that, and I know that they use my group's research. But they're the ones making those decisions. They're the ones making assessments of risk. And yeah, so all I can do is report that they have identified those regions as candidate landing regions for the first missions of Artemis.
Well, imagining this is the first landing zone and it works out great, is that where they're going to build the lunar base? Or perhaps someplace else?
Again, I can't speak for NASA, but they have been exploring a variety of lunar bases in the South Polar region. One of them that they've mentioned in open meetings is within the Hallworth candidate landing region, but I'm sure there are others. Those deliberations they are making in private, in confidence, and so I don't know what other factors or features they're considering. I can speak to what my own group has been doing. So we did in the last 2 years some assessments of hazards within the South Polar terrain, and one of those hazards is landslides and rolling boulders. And there's two sources that can cause those landslides and boulders to roll. And those are traditional moonquakes produced by fault movements. And there's two large faults in the South Polar region. And we've modeled the intensity that those faults can generate and the damage that they could produce. And also you can have impact events that also create seismic activity. And so you would in general not want to be near slopes where landslides that are prone to landslides or rolling boulders. In one case in Schrödinger, we actually tracked a boulder that rolled well over, I think it's 15 kilometers. It just kept rolling and rolling and rolling, of course, down slow. So you want to be mindful of those types of hazards when selecting a site for a moon base. I should add that those types of seismic activities also affect the moon base itself. You have to design your structures to withstand seismic shear. And so I helped a graduate student, a PhD student in Australia, actually, did an engineering study, and it actually changes the shape and the wall thickness of habitat structures to withstand those seismic shear structures. So that's what I can say about moon bases.
Thank you.
Anybody else?
Great talk. Great
Yes.
talk.
On these early missions like the one you have here, how long would the astronauts likely be on the lunar surface?
Okay, that's a great question, and it's also a question whose answer is in a state of flux. And so when NASA asked us to do the study on Malapert, that is when NASA was using an orbital gateway station. Okay, and that gateway station was in an orbit that only allowed the astronauts to abort or to come up and rendezvous with the station at certain times. And so in that configuration, once the astronauts landed, they were required to stay on the surface 6.5 days before they could launch to rendezvous with Gateway, which is where the Orion return vehicle was stationed. Okay. Now, Gateway has gone away in the new architecture. That means that there is the potential of Orion rendezvousing with the lander in a different orbit. And depending on the orbit that is selected, they actually may be able to have shorter missions. And in case there's an emergency, having an abort to rendezvous at any time or in a more frequent time, you would think would be favorable. So I can't answer that question because the architecture is under review.
Thank you.
Now, Alberto?
Well, first of all, thank you very much for your talk. It was very informative. I understand that water ice is highly likely to exist in permanent shadowy areas with all that implies as a resource. But how we can be 100% sure that there is water ice in the chosen location?
Yeah. So let me say a couple of things about the evidence for it. So we know from the rocks that the Apollo astronauts returned and some lunar meteorites that the lunar interior has water, and so it was occasionally volcanically degassed. We also know that large asteroids and comets can deliver water, and that those deliveries would have been particularly abundant during that early period of bombardment. And then we have spacecraft data that address this issue. There was a mission called LCROSS that plowed spacecraft into Cabeus crater, and spectroscopically, water was detected, and it was estimated based on that measurement that there was up to 5.6 weight% water in the regolith. And then water has also been detected multiple times using remote sensing techniques at the surface of the moon, but that can be misleading. The water they're detecting is in the upper few nanometers of the lunar surface. It says really nothing about bulk abundances, and so the evidence there's evidence, but it's definitely needs to be tested. Right. And so that gets to your second question. How do they do that? And the way that's going to be done is it's going to be done robotically initially, or in some of it's going to be done robotically, like NASA's Viper spacecraft. There's another what we call commercial lunar payload services mission. In fact, it's going to happen this year, going to land right in that area on Connecting Ridge that I was telling you about. So when that mission occurs, you'll already be familiar with their landing site, and they're hoping to drill into one of those PSRs. So that is one way to approach it. And then the crew, when they begin on the surface, will also explore some of these PSRs. I didn't have an opportunity to illustrate that in the EVA, the Malapert EVAs that I demonstrated. For time, I illustrated what they could do with the long EVA 3, but EVAs 1 and 2 were designed to explore small PSRs around the landing site. So they definitely need to get what we call ground truth.
Okay, thank you.
Yeah, I have one more question. How many astronauts are going to be? 4? At least 4? They're going to work together at the same time, or how many it's going to be?
The Orion capsule was designed for 4, and during the Constellation program, that's the program that preceded Artemis, it was designed to land all 4 astronauts on the surface. And in fact, in Constellation, the architecture was the following. First, 2 pressurized rovers would be delivered to the surface. Then the astronauts would launch and land once the rovers were there. And then the rovers would allow them to operate for at least 14 days away from the lander. And so they could explore quite a large region inside the rovers. And the rovers, they don't need to be in the spacesuit because it's pressurized. So they're just working in shirt sleeves, right? The only time they need to get in the spacesuit is when they need to go outside to collect a sample. And so we demonstrated in a series of lunar mission simulations that greatly enhanced productivity and greatly reduced the risk to crew. And so that was the Constellation architecture. Our Artemis has decided to have walking EVA for a couple of missions before they develop the rovers. And in fact, they're going to land an unpressurized rover first. And the astronauts have to work in a spacesuit in that vehicle. It's kind of like Apollo 15, 16, and 17. And eventually there will be a pressurized rover. So they have a different mission architecture for Artemis. Okay, having said all that, I think I've walked away from your question though, and I'm not sure if I answered it or not.
Yeah, well, yeah, I have an idea. The rover only can carry 2 astronauts, right?
Oh, yeah. So I'm sorry. So in Constellation, the idea was to land all 4 astronauts, and 2 would go in each rover.
Okay.
Okay, and 2 rovers provided redundancy. So a rover could, in an emergency, support 4 astronauts, but the idea was you would have 2 rovers, and that was your redundancy. So you could bring 2 rovers back to your lander, or if there was an emergency, bring everybody back in 1 rover. Okay, and these rovers, astronauts are only going to be on the surface like 10% of the time, and so these rovers could then be telerobotically driven from Houston to continue exploration between landings. And so that was in any case the plan. Now with Artemis, we don't know.
Okay.
We don't know.
Thank you.
All right, David, that was great. I really want to thank you for that presentation tonight.
Yeah, well, my pleasure. As I said, it's a delight to speak with this group. I mean, I've obviously known about your group for a very long time. I spent the first half of my career in Tucson and in and around Flagstaff, Lowell Observatory forever. So I'm very aware of the contributions that the amateur observing community provides exploration. And so, yeah, it's been a pleasure to meet and speak with you.
Well, thank you very much. All right. All right, everybody. I want to thank everyone for joining us tonight. How about you want to see that video one more time? Anybody? The music video? Yes? No? Yes?
Yes.
See how it's going. Okay. Here we go. Get back here.
We look up when the night is clear, chasing worlds that feel so near. Moonlight dancing in our eyes, planets drifting through the skies. With every sketch and every view, we find a little something new. A quiet night, a patient mind. The universe is what we find. From stargazing to science, we follow the light, turning wonder into wisdom in the silence of the night. From stargazing to science, across the endless blue, every eye upon the heavens brings the universe in view. Jupiter's bands and Saturn's rings, meteor trails and comet wings, lunar shadows, solar flame. Every observation has a name. Not just dream and not just art, but careful work from every heart. Amateurs with purpose rise, measuring the changing skies. From stargazing to science, we follow the light, turning wonder into wisdom in the silence of the night. From stargazing to science, across the endless blue, every eye upon the heavens brings the universe from the world around, where curious hearts and minds are found. With telescopes and notes in hand, together we help understand. No one watches the sky alone. In ALPO we found a home, a family joined by what we see and what the heavens teach us to be. From stargazing to science, we follow the light, turning wonder into wisdom in the silence of the night. From stargazing to science, with the ALPO family too. Every eye upon the heavens brings the universe in view. One small telescope, one steady hand, one report from where we stand. Piece by piece and night by night, we help the world understand the light. From backyard skies to data shared, every careful note prepared, we turn our wonder into more and open up the cosmic door. From stargazing to science, together we climb, linking earth and sky above, across the halls of time. From stargazing to science, the ALPO family shines. With every star and every world, we cross the cosmic lines. Look up, take note, believe what you see. The sky is waiting patiently. From stargazing to science, that's where we're meant to be.
All right, that'll do it for this meeting. Again, I want to thank everybody for their attendance, and we'll see you here next year.
Yes. Everybody be safe out there.
Yeah.
Thank
And
you.
congratulations to all the award winners.
Yes.
Thank you. It
Thank
was
you
a real
for a
good
great
talk.
meeting.
Yeah,
Loved
great
it.
job, Tim.
Thank you very much.
Good work, Tim. Yep,
Thank you very
yep.
much.
Cheers all. Be healthy.
You too.